the mean value of that. So, that was a weird message. Okay, either way. This is the model. Some people estimated some parameters from this model. So we get to the next time point by taking the previous values, multiply by a matrix, and then we add some noise to it. Let's just consider that white noise. We'll get back to the definitions of that, but just consider it independent normal distributions. And the covariance structure of that is written like this. And you have the numbers here. The covariances are fairly large in this case, which makes a lot of sense from a physical perspective, because you have, in the gas, you have a balance between the two different forms of nitrogen oxides, or NOx. So assume that we have measurements up to time 9 o'clock was today, time t. How do we project the future? So what we have to do is to forecast the prediction at the next point in time. As mentioned earlier, the forecast should be a mean value and a variance covariance of that. Now, what I will state now, and I will repeat that many times, is that the best predictor is the conditional expectation. It's too slow. I will swap. So the best predictor is the conditional expectation. So the forecast we're going to make, expectation of xt plus 1 given xt, we plug in the expression that we have up there, and then, well, the conditional expectation is a linear operator. We just do it by terms. And the first term here contains something with x. Conditional on that is still just x, but the expectation of the noise is 0. So the conditional expectation is just making one step forward. Now the variance covariance of that, that's the variance of the true value minus the expected value. And we can plug in, as before, the expression. Notice here that this term cancels out with that term. So the deterministic part, so to speak, of the model cancels out in the variance. That's not unlikely. That makes somewhat sense. The only thing that contributes to the variance on the short term is the added noise, which has covariance matrix just sigma that was defined initially. Now, this is the R code that does that. Basically, I won't go through the details now. Often, I will make live code sessions as well, just to take them step by step. Here, the calculations are fairly simple, so I'll just give you the results from down there. And the variance of the error is kind of trivial because you just have to restate sigma, which was kind of given in the definition. So equal sign there. Just make 2 lines under that. You're done. Now, the tricky part is that we arrive to time 12, and the measurement of nitrogen oxide fails. But we did get an observation from the nitrogen dioxide. So what can we do now? Can we make an estimate of the missing observation? We just, on the slide before, we made a prediction. We also made a prediction of the one that we observed. So we predicted 61, we observed 67. Is that good or bad? Well, what we did was we predicted something, and then we observed something that was slightly higher. So given that there is a large covariance between the two, what would you expect to be the case for the nitrogen oxide that we did not observe? What would make the most sense? It should be higher. But how much? I don't expect an answer to that. But I expect that we find an answer to it. And I also want to find the variance of that expectation. Bang. So what is this? This is why I wanted it to be on the other side. Let me see if I can just... yeah. So you have the linear projection theorem right here, right? That's what we want to do. Because we want to do the conditional expectation of the second state given that we observed only the first state. That's what we want to do. And then we also condition on what was there previously. So, we'll do this. What we want to care about is the expectation of the second state at time t plus 1, given that we observed the first state at time t plus 1, and we know the state at time t, or we observed both. So what we have to do is that we have to look at this here. That's pretty much just rewriting it with a parenthesis there, and then having the expectation of a conditioning on xt written as the last term everywhere. So in the remaining part of this, just keep this one out here. That's conditioning on everything that was prior to time t plus 1. We'll just keep that everywhere, but focus on the other parts. So what we need to have here is the expectation of x2 as the expectation of the variable that we want to care about up there, given all the previous information, plus the covariance between x1 and x2, given all the previous information. And then we have the variance of x1 inverse. Then we have x1 minus the expectation of x1 given all the previous. And if we take from the definitions over there, use a phi1 up there, take the elements in that matrix 1, 1, and 2, 2, and so forth, then we can actually just plug in the expectation. We have that there. The expectation of the second variable is the first variable times 0.4 and the second variable times 0.8. Right? That's what we have here. And then we have the covariance between the first and the second element times the inverse variance of the first element times the observed value of the second element at time t plus 1 minus the expectation of the first variable, which is what we calculated previously, 0.9 times what was there before, plus, so minus 0.1 times the value of x2 at the time before. And that was it. That's the prediction. That's the estimation. So basically what we have is what we had as the prediction before plus a correction here. And now, since this observed value was above the predicted value, and these are positive, we will indeed, as you said, get something higher. Now the variance of this, well, you just have to go into it again and say, what is this? The variance of x2, expectation of the variance on x2, condition on x1 and xt, is the variance of the prediction that we had just before, and then comes minus some covariances. I won't get into the details of this. The covariance of x1 and x2 squared, and then the inverse of the variance of x1. But what I will just stress is, what is the intuition about this? The intuition is, well, when you do this, where you say, I want to improve my information about something by using information elsewhere that is connected somehow by a covariance matrix, as is given over there. What you get is that you get the original prediction variables, and then you reduce that by some number. The larger the covariance between 1 and 2 is, the larger reduction you get. On the other hand, if sigma 1, 1, as in the one that you condition on, has a large variance, you get a smaller adjustment. And if you plug in the numbers, then you get a prediction that was not 90 something but 102.9, and the updated conditional estimate of the variance is 0.95. Remember, before doing this, our prediction was 23 for the covariance. So we get, in this case, a huge reduction in the variance estimate of the unobserved variable, because we did observe the other, and because the covariance between them is so large. That is, of course, not always the case, but you will, in general, get some information and thereby reduce the variance. So I tend to always have a slide at the end saying, these are my highlights. You can always look at that later because you have the handouts. Exercises for today are chapter 2, 1, 2, and 3. There's one thing that is not written correctly in exercise 2. That is that it states there that x and epsilon are uncorrelated. It should say independent, as we discussed earlier. So, any questions? Any general questions? Yes?
This pollution problem, that was a reference to the Volkswagen scandal, correct?
Yeah. And all the others. But these data are old, they're from before the particular engines were made. But I think that's one of the difficult things, what you do about things. But that's a more political discussion, I think, than a time series analysis problem. It's a matter of how you test things. I can say what my personal thing is, but only after